Okay, so welcome everybody for the first condensed matter seminar of the year. So we're very happy to have visiting with us Nirmal Ghimire from University of Notre Dame. Nirmal got his PhD at the University of Tennessee with Dave Mandris, who's a very famous crystal grower of quantum materials. He also worked at Oak Ridge while he was there with some good neutron scatterers. Then he moved on to Los Alamos lab, working with Eric Bauer, and then to a director fellowship at Argonne National Lab, working with another great crystal grower, John Mitchell, and then onto a faculty position at George Mason. And then he decided he really missed the football culture of Knoxville, so he moved to another great football town, South Bend, to University of Notre Dame. So Nirmal, really happy to get that.
Thank you, Ken. Thank you so much for this invitation. It's so nice to be here and talk about my research a little bit. And it's as Kemp said that I've been trained to grow crystals, but I did my PhD in condensed matter physics. So it is a blend of this material synthesis technique and thinking about physics. How can we leverage this? Because we cannot do condensed matter physics without materials, and we need the crystals. And with the crystals, how can we think of designing these properties in the materials? Is the theme of this talk. And I'll try to give some examples, of course, of the work that we have done recently. So, I'm part of this Stavropoulos Center for Complex Quantum Matter at the University of Notre Dame. This is a recently established quantum center, and the plan is to hire about 8 or 9 faculty for this quantum center. 5 has already been hired, and then there is a call for 2 open positions going now. Right now, I think that call has been open. So it's great to be at the Quantum Center with so many people thinking about similar ideas and especially in condensed matter physics. So my work has been funded by NSF Department of Energy and Office of Army Research as well. I want to acknowledge them. So first of all, the overview of this talk is that I'll briefly go over to the background why actually I am interested in quantum materials. Maybe that can help some of the graduate students. How many undergraduates are here? Very good. And then graduate students, right? Some of you, it can help you, get interested in materials and so on. And then I'll talk about different materials. Then I'll show you how, we use this design principle to find some properties on the various different materials. There are basically these 3 different materials where I'll show you how sequentially we can think about designing materials and what we have got. Then I always like, when we write proposals and things like that, faculty know it better. This is more exploratory. People don't want to, put money on exploratory things. But sometimes with the exploratory research, you can find something new that you have not thought about before. So this is an example. So I just wanted to present this one also. If time allowed, I'll get to that point. Okay, so the quest for new materials. We are in materials world. We know that materials exist everywhere. Now the question is, why do we want to find new materials? We are always trying to find new materials, right? And the reason is, this is a great picture. I took it from a report that was submitted to the Department of Energy. And what it shows is that it shows our human, civilization. Actually, we were, in this Stone Age, and think about what people might have used at that time and what the life could have been at that time, right? The stones, they were using for many different purposes for that one. Even hunting, protecting themselves, building houses, everything. The best available material was stone to them. Even fire wasn't discovered at that time. Going from this Stone Age to Bronze Age, now you have something that's more reliable. You can make utensils, you can start doing farming, you can make better weapons, and so on, right? Life became easier. Civilization moved forward. Now fast forward with the Iron Age, there was the age of industrialization that helped human civilization. Now we are in silicon technology since 1950s when the transistors were made out of some silicon compound. Then our whole civilization had changed. Computers in 50s made of vacuum tubes were used like a house. Now we can use our phone. They act like a computer, right? It all came from these new materials and then engineering the new materials, designing the new materials for a particular purpose. Now we know that the silicon is hitting a limit, right? That's why we need new materials if we want to move our civilization forward. And what is that next material? We don't know that, right? So we need from all points of view, from theory, experiment, designing, synthesizing, we need new materials. That's the quest for new material. And that's what we're working. And my approach to do that is, as I mentioned, is to grow materials in the lab and grow these materials to understand the property, and then that will help us, make or design the new materials that is coming along. So these are the pictures of different crystals that I or my group synthesized over the course of the time. These crystals, are all bulk crystals grown by various different methods, and sometimes, we can live with tiny little crystal. Again, the definition may be different. If somebody is making with nanotubes or nanoflakes, that's very different definition of size of the material. In our case, for example, if Kemp is doing inelastic Newton scattering, he needs big sample. These crystals were actually made for this reason, because you need a lot of mass, and then you need large crystal. These crystals were flaky, and my collaborators were able to kind of exfoliate them to monolayer, bilayer, and then it enabled them to access this physics in monolayer and bilayer. These are the crystals that we can handle, easily grown. We can handle with our hands and try to measure transport properties and so on. These crystals. Now the question is, how do we grow these crystals, right, in the lab? There is no single way of growing a crystal. It all depends on the phase diagram and different things. Sometimes you need a lot of time in the lab, try and work it out and see if it works or not. But the main tools that we use in mostly is what it's called flux method. In the flux method, what we do is we dissolve the elements in a metal. For example, tin has a low melting point. It melts about 300 degrees C, and then boils above 2000 degrees C. So it acts as a solvent for many different materials. So you can dissolve other materials and then heat it up to maybe 1100, 1200 degrees centigrade. When everything becomes solution, they interact with each other, and then you can cool down and precipitate it. Have you tried crystal growth at home? How many? Yes, crystal. You can do that. Actually, you should try to do that. My 5-year-old girl already made crystal at home because her father is a crystal grower, right? You can go to Walmart or Target. You can buy crystal growing kit. Try to do that. You can get alum, and then you dissolve it, and in overnight or 2 days you get crystal. Good science activity at home for your kids as well. Okay, this is because I mentioned that because you can. It is basically the same principle. You don't need to heat alum. But in this case, we need to heat it because we need to melt the metals inside a metal and then precipitate the crystal in the crucible. Then there's a small little capsule here. We use that as a filter when we kind of invert it and then centrifuge it. We throw out the flux and then we get a beautiful crystal. Okay, that's one way of growing crystal. We need a furnace like this. There's another way. It doesn't work all the time. Sometimes you can grow crystal only by taking them in vapor form. For example, you have powder, and then you mix it with some very reactive elements, just like iodine, bromine, and these elements will react with these powder and take them in vapor form. And if you can maintain the temperature gradient from these vapor pressure builds up here. This is a hot end, this is a cold end, and then these in the vapor form, these material move from here to here, and then deposit crystal in this end. And look at the nice crystal here grown that way. It was grown in a quartz tube. You need a temperature gradient. This is a 2-zone furnace that we have in my lab to grow this way. And sometimes you can change the temperature. That's the Brisbane furnace. What you need to do is there is a motor attached to it, and you can pull it up and down. So you put your tube here to grow the crystal, and then through this thermal gradient you pull the crystal up. You melt everything, and then you change the temperature that way, and then you grow the crystal. Okay, that's another way that we use. And sometimes this furnace can go to 1200 degrees centigrade, but sometimes you have to melt your material at 2400 degrees centigrade. What do you do? You can sometimes design your own, right? That's a modified version. I designed this actually when I was in Los Alamos.
What's the fan for?
Very nice, because see, the temperature here is almost 2400 degrees centigrade, and since this was hand designed, we wanted to cool, because this is a quartz tube here. See, we don't want this quartz tube to be melting. So see, there is a water line here. The water line is cooling this and this part, and you still want to keep this preventing from melting, right? Otherwise, then that's a disaster. Sometimes these little tricks help, and it worked. We grew crystal that way, and it was grown in a very thick tantalum tube. It was a 3 millimeter thick tantalum tube, because there was sulfur and samarium inside it. Both are very volatile. So putting sulfur, which has a boiling point of 150 degrees centigrade, and then going to 2500 degrees centigrade, you are making a bomb. You need to confine in a very thick tantalum tube. It was 3 millimeter tantalum tube. You can see actually it was bulged when we finished the reaction. It was actually bulged like that. Yeah, sometimes you have to, make your own furnace. That's an example. Or
so the lab doesn't get too hot by doing
this? No, because this is a RF coil. It hits only at the center. Here you don't even feel. You can stand here. Of course, when it was 2400, we were far away with glasses, and we were measuring temperature with pyroscope. And then this is called Sosarsky technique. This is a very neat technique. Again, you can melt metals, and there are these 4 arcs called tetrarch, and everything is melt. Then you put a rod there, and then you slowly pull the crystal out. So if everything works out in an hour or so, I'll have this big crystal. Okay. So if I have to go back and show you, these different. This was grown by vapor transport. This was the Brisbane, where we changed the temperature. And these were grown by flux. This was grown by Sosarsky. This crystal was pulled just like that by melting, and these were also the vapor transport. So these are the different things that we use in my lab to grow the crystals. Now, all these are the technical things, right? So the most question is, again, I'm by training physicist, right? But I have to do a chemistry work also. So what are the design principles? How do we think about designing the materials? What are the basic ingredients if you want to think about designing the materials? And then first of all, you need to have a good chemical intuition, right? About the element and so on. Some are magnetic, some are not, and so on. Some have bigger size, some have smaller size, and they all help you in designing the crystals. Structure. This structure means not the overall structure, but it's a layered compound. Can you go down to like monolayer, bilayer, or it's a bulk material? That also is a design principle. What kind of physics you want to do with these different materials. For example, this is a picture of, or is a structure of a layered compound. You can just peel off layer by layer, right? Or atomic arrangement. For example, here, if you look at the black atoms, these black atoms are arranged in a corner-sharing triangular pattern. This pattern is called kagome, which I'll be talking about a lot in this talk today. So this atomic arrangement also gives certain properties to the material. Okay, and another thing is the structure itself. For example, this is a classical case that I have iron germanium is one compound. Depending on how you grow, it can grow into 2 different phases. One becomes cubic on the left, and another becomes the hexagonal, right? The cubic one doesn't have center of symmetry among these atoms. You can see that. If you look here somewhere, you can invert all these atoms and get this position. It lacks the center of symmetry. Lacking of center of symmetry can generate some properties that a center symmetric crystal cannot have. So that's another identity. And this one does have center of symmetry. So their properties from that standard point of view is also different. Okay, these are basic design principles. Now, what is this part? What are we doing with all these, ability to grow different crystals, and then these, tools that we can think of? Is right now, what my main project has been on to working on materials at the interface between magnetism and electronic structure. And that is what I'll be talking about, in this talk. That's just, a picture that I made just for the illustration purpose. Okay. And now, what kind of material are they? And this is the idea that I've been working for the past 7 to 8 years. And I'll kind of go over to this. This is a kind of magnetic structure that was discovered in 2009. If you are familiar, this is called a skyrmionic texture. You see how the spins change from one layer to another layer. They change their direction. So in this kind of texture, what happens is that when electron move through this texture, the electron can pick up a geometrical phase. I'll show you an example. When something pick up a geometrical phase, they have to move through this three-dimensional stuff. See my hand here. Everybody can see my hand. So I'm putting my hand like this. Look into my thumb. So I'll move my hand in three-dimensional way and see what happens to this orientation of this finger. Okay, we go here like that. I'm not twisting my arm. Okay, I'm just moving in three-dimensional space. Did you notice what happened? I'm not twisting. Did everybody notice what happened? I was this way. So by moving into this three-dimensional space, it picks up a phase, and that phase is basically a Berry's phase. And then that Berry's phase is a topological feature in the material, and you can pick up by measure. It acts as a fictitious magnetic field, and then because of that fictitious magnetic field, electrons get deflected, and then you can measure those even with transport measurement like Hall effect. This is one of the thing that these kind of non-coplanar texture have given to us. At the same time, if you have this type of electronic properties, this is called a Weil semi-metal, meaning that these are just like a lot of people here work on graphene, right? They have Dirac point, and then Dirac have spin up, spin down, degenerate. If you lift that degeneracy, you get in momentum space these points that are called Weil points, and the Weil points act as monopole in the momentum space. So there is a Berry flux from flowing from one monopole to another monopole. Because of that Berry flux, you can still get this anomalous Hall effect in this kind of material also. So while working on this system, was going through the literature and found that actually these were the recent discoveries, right? 2009, 2014. But these are the stuff that was discussed, even earlier than that. Especially Gregory Volovic has spent a lot of time in describing this interplay between real and momentum space topology. That comes here. You can see that this is a real space topology, that the electron is picking up this Berry's phase completely from the real space ordinary of magnetic moments. Whereas if you go here, this is all momentum space phenomena, but the result is the same. They're picking the same Berry's phase, right? And then here they discuss that you can kind of correlate these real space and momentum space topology, and then you can get some new physics from it. This has been discussed in this article or in this book. And actually, this real space equivalent of this is a monopole. See, all the spins are pointing in this in the same direction here, right? It's a haze hog in real space, and that haze hog is a skyrmion. And this kind of thing were already discussed in these books way back before the discovery of this phenomena. Yes.
Was this for superfluid helium?
Yes, sir. Yes. That's discussed the universe in a. I like this book. I don't know if I have understood this book properly reading through it, But I like this book such a way that there is so much of physics in there that maybe we can try and test in materials. For example, these things, right? The interplay between real and momentum space topology. And that is my guiding principle for the research. And all the talks that I'll be showing is to try to get towards that direction. So this is a bigger frame, and that generates my interest. Okay. So there has been, and it's nothing like people have not thought of. I found this when I was working on this. I found this article pretty neat in a sense that what they tried here is they took a graphene. This is a toy model theoretical study. It was done in 2015. And what they did is they took a graphene and put a skyrmion on top of a graphene, like theory, because they can do anything. And that's how actually Haldane writes in his Nobel lecture that he was, when he was writing that PRL, he was doing science fiction because graphene was not, exfoliated at that time, and he was talking about magnetism in it, right? So that helps sometimes, and that helps us to design the materials also. So here you take a skyrmion and put a graphene and put a skyrmion on it. These are the graphene bands, and what happens because of the topological nature of the skyrmion, it opens a gap in this place, and there is a Berry curvature here. And because of this Berry curvature, you can see these edge states coming in the gap. And then because of that edge state, it quantizes the Hall effect. So this is a way of probably getting a quantized Hall effect, right? Even without applying magnetic field. And then the question is, can we engineer a material that allows such interplay? This is, again, my guiding principle, and the material system that I have chosen is in thinking and keeping all these things in mind. And the material system that I am currently studying is this kagome system. In kagome material, what happens is that you have these triangles of atoms that are corner sharing with one another and perfectly making this hexagonal arrangement. This is called a kagome. And in kagome, what happens is that if you have a magnetic ordering, for example, this antiferromagnetic ordering, right? This spin is pointing up, this is pointing down. Now, because they have the equal interaction with, the third one will have equal interaction with this, so it gets frustrated whether to point up or down, and then you get very highly frustrated system in a kagome system. And it can you can tune that with magnetic field and so on, so you can get a whole host of magnetic phases in kagome system. Another interesting feature of these kagome, again, it is a single layer of kagome system. A band structure looks like this. That it has flat bands. It has these Dirac crossing here. They coexisting in a same system. These are two extreme limits of a band structure. They can come together. They can be both topological. Especially recent interest has been in the Dirac point, that if you can open a gap at the Dirac point, similar as in graphene, you can actually get the quantization of the Hall effect. This is one of the kind of highlights in Haldane's this Nobel lecture that is kind of published and it's his work from this paper, right? What he showed is basically to a graphene, and graphene has this type of Dirac points. And the gap can be opened in this graphene by two ways. One, by breaking the crystalline symmetry, and if you break open a gap by breaking the inversion symmetry, then what happens is that these bands are tossed with one another. It's nothing interesting, right? Valence band connects to valence band, conduction band connects to conduction band. Nothing interesting. But when the gap is opened by breaking the time reversal symmetry, then the edge of the valence band touches the edge of the conduction band. That's a new state. Because of that state, now that's where the quantization of the Hall effect that can come from. And this kind of physics can be realized in here as well, right? If there's a way to kind of open a gap, but here you need a single layer of kagome, which is again a difficult thing to do. What we are working mostly on is on the bulk material, but it's not discouraging, because even in the bulk, right? If you have a Dirac node, you have spin up, spin down bands degenerate. You can here you can break either time reversal symmetry or break the inversion symmetry, and you can isolate these or split these spin up, spin down bands. Because of that, now you have a wild nodes. Now it's an interesting system to work with. And as I said earlier, that the real space equivalent of these wild nodes is a skyrmion. Now, can we crystallize skyrmion out of these in a magnetic system where that have these wild points, or vice versa? Is an interesting question. And this kagome system can be an ideal platform to work with, right? And there has been some concrete theoretical work also. For example, in this case, what Liangfo's group did is that they took the topological insulator, and then they put a ferromagnet on top of it. Again, theoretical study. And what they found is that because of the topological properties of the topological insulator, it modulates this magnetism here, and instead of being just a simple ferromagnet, these kind of skyrmionic texture form here. And depending on the parameters, anisotropy and so on, what happens is that it can either form helix or skyrmion and so on. So the crystal parameters are important in that case. And again, the idea is, can we kind of play in our system, real material system, with these things? Can we tune the anisotropies and drive these skyrmionic texture or other spiral texture in this material system? So, when thinking along this line, these are the recent works on, yes?
In the previous bit, so how is that dependent on the geometry of the lattice? Or the topological, yeah.
Not on the geometry of not in this particular one geometry of the lattice. Maybe the anisotropy of the system or other parameters that I don't know completely off of my head. Okay, but you can change. You can find this paper. They change some parameters, and instead of getting this skyrmion, they get helix. Okay, there are certain parameters that they can tune with. And what I
so the skyrmion is the ground state or is it excitation?
It's a ground state. And then the way that what I was trying to say is that in the material we can change the parameters in terms of either we can change the lattice scale, we can change one element from the other element, we can change the interactions, magnetic interactions, right? And is that a way to kind of crystallize this kind of things?
So the magnetic layer by itself is a ferromagnet holding out.
Yes.
So why would the topological insulator pulls down?
The charge from here goes, the topological charge, when they move from this topological insulator to the magnetic layer, they deform these texture in such a way that they form this skyrmion. There is an interplay between these charges and the spins. The topological character that they pick from this, the topological electrons carry, the influences these orderings to form these deformations.
So those electrons in the middle of that Dirac point, the wave function overlaps with the wave function in the ferromagnetic layer. That would give
I think that is the I don't know the every details of how they wrote the Hamiltonian and things like that, but yeah, in essence that's the thing.
By charge, do you mean the topological edge states, or is it the bulk of the
Topological edge states?
Okay, that influences the spins of the
Yeah.
Okay, thank you.
All right, that's why you need topological insulators in this case. Okay, so now there has been recent interest on the kagome system that did all these high-profile papers because here you have very known collinear magnetic state that generates this large anomalous Hall effect. This material also has been shown to be to have these wild fermions in this material. This material has these two sets of Dirac points, and when the gap opens by magnetism, it gives large anomalous Hall effect. Same story with this. This is a wild, magnetic wild metal, and this iron tin. The first time it was shown that both these flat bands and actually these Dirac point coexist in this material. And although we have these many materials, when I was trying to work on this kagome system, was starting as an assistant professor, trying to find some new system to work. These are very inflexible systems, in a sense, except this manganese thin, maybe you can get manganese with germanium and so on, but if you go from manganese to iron, the story becomes different. In iron 3 tin 2, if you try to replace iron with cobalt or something, or try to change the tin, then it does not grow or it doesn't form in the same structure. Same thing with these two materials. I think they were trying to dope some indium here, but not more than that. So when I am telling you that we need a material that where we can sequentially change these different properties by changing the different elements, we need a more flexible system. And I came to, with this regard, what I found is I found this system very interesting. This system of material. It was known in 80s and 90s. Basic property were measured, but not studied, well in terms of magnetism or topological features. But this system has, the black atoms are manganese atoms, and these manganese atoms are the ones that form. If you look from the top, you see like this. These are corner-sharing triangular atoms. This makes perfect kagome layer. But this kagome layer are stacked vertically along c-axis, and when you look carefully, what happens is that this layer and this layer have only these blue and red are tin atoms. The reason for a different color is that they sit in different inequivalent crystallographic sites, so they are inequivalent tin atoms. So is this gray ball. There are 3 tins, that's why. And then there is R can be different, right? From rare earth element, it can be yttrium or even scandium and so on. And then these layers are separated by a block that's only contains tin. These two layers are separated by tin and rare earth containing element. So in itself, this is a very interesting structure. I'll kind of discuss about that. The nice thing about this structure is that if I replace, we have so many rare earth elements, right? These many rare earth elements and scandium and yttrium as well. You replace any of these elements here, it forms the same structure. You can change the manganese with any of these 3D elements. You get the same structure. Then you can replace even this tin with these 3 other elements. You get the same structure. So you have multiple choices to tune the properties of this material. And this talk is mostly about that today. Okay, how we did that, and what is the property of the parent compound and how this has been tuned. Yes. Any question here? Yes.
So it's the stoichiometry that's setting the structure?
Yes.
Oh.
Yes. The stoichiometry that is setting up the structure, and we can replace that with another element. It doesn't care. So that's why I said
166.
It's 166. It's a very nice system to play with. Okay, that's why this system has been very popular recently. And when I was working, there weren't many people working on this system that time. Okay, so now the interest when you have these 2 blocks separating, there is another additional property to this material is that, see, the interaction between these 2 layers will be different from the interaction between these 2 layers, right? Because they are separated by 2 different blocks. And if you add on the next nearest neighbor interaction, which is J3, then you have frustration along the c-axis. In this material, the in-plane is strongly ferromagnetic. But then there is an inbuilt frustration, we call it parametric frustration because it comes from the parameter, is pretty nice. And you can play with that even by applying magnetic field. And you can generate a lot of different magnetic phases. And you can study how the properties changes from one phase to another, how they influence the transport properties, especially the electronic band structures and so on. In this talk, I won't have time to discuss on the topological bands of this material, but yes, they do have this Dirac feature. We have our own data also, other people have also measured. So they have these Dirac cones and so on, very close to the Fermi energy.
In this case, the J3 will be in the same order of magnitude of J1?
No, this is much smaller.
By how much?
I had that number, maybe by an order of magnitude smaller. But it definitely plays a role. Okay, it definitely, if you don't, if this is, I will show you later. When this is not effective, it becomes simple antiferromagnet. Okay, when this becomes effective, it becomes spiral. Okay, this material is like that. You look at it, the phase diagram. It starts with antiferromagnet. So J3 is weak, maybe at high temperature. And then when J3 kicks in, it modulates into a spiral phase. So this is we call it distorted spiral because this is the magnetic structure at this phase, which is the DS is distorted spiral. What happens in this case is that these are these different 9 layers because these spins are ferromagnet in a plane, and when you go to next layer, it kind of changes a little bit, and then it repeats after 9 layers, which is about 4 unit cell in this case. Okay, when you apply magnetic field in this direction, actually they distort a little bit. That's why, as a function of magnetic field, we name this as a distorted spiral. And then you apply magnetic field, further magnetic field into this. What happens is, in this case, when you go in this case, these are just the Q vector we observed from Newton diffraction, but it's not relevant for this talk. You see here, what happens is that it's very interesting. The moments are in the plane. You apply magnetic field in the plane. You first distort them a little bit. Then what happens is that they find easier to flop out of plane. So they just go out of plane. And since the magnetic field is in this direction, they will cant them a little bit. And it still maintains the spiral state. So it becomes a transverse conical spiral state, just like a somersaulting spiral, but a little bit canted. And then you apply more magnetic field to this, right? Then the energy, it's all interplay between these different interactions and the magnetic field. That these spins find easier now to flop back into the plane. That's what it happens here. You can see all these changes. You can measure them in magnetization. You can see them in Newton diffraction experiment. And then when they fall back, they rotate in a different way than they started with. And this is not a helical state now. This is a fan-like phase. See, it does not rotate like this in this case. It rotates, it makes a complete rotation and comes back here. In this case, these two rotate together, and then they again come back. They go like this, they come back. That's why this is a fan phase. We call this fan-like phase. And then they become ferromagnet by the magnetic field, force ferromagnetic field. So it has a very rich magnetic phase diagram because of these competing interactions. We can tune them with the external magnetic field and get these magnetic fields. What is the highlight of this material is not just only this magnetic phase. The highlight is that in this transverse conical phase, which appears, and particularly at high temperature, above 100 Kelvin or so, what is observed, we observed that at the same time there was another group also that reported it, was that there is a topological Hall. That, Hall effect, you have these usually 3 components in a near ferromagnetic system. One is the normal Hall, and that's a Hall that every material has this, transverse deflection, right? Because of the Lorentz force, you get the normal Hall. Then this anomalous Hall is usually proportional to the magnetization. Does not always have to be proportional. Now we are understanding this. There are new materials where it doesn't care. You still get the anomalous Hall. But in most of the material, it's proportional to the magnetization. That's the anomalous Hall. On top of these two, there is another topological Hall. That topological Hall usually comes from these electrons moving into these non-coplanar texture. So you need to have this scalar spin chirality defined at least 3 different vectors in 3 different directions, so that in the electrons will have this geometrical phase. This comes from the geometrical phase. That's why this is named as the topological Hall. This topological Hall was observed. You see here they did a better result than ours, so we didn't have to do it. So here they it is concentrated mostly at 250 Kelvin, and then it starts above 100 Kelvin, and there is no topological Hall at lower temperature. If we kind of look this region and map into our phase diagram, it mostly like into this TCS phase, which is this phase. And this phase is just a conical spiral, right? So a spiral state does not give a topological Hall because you don't have this third vector to it. And that's why we don't see it at low temperature. Now at high temperature, my theoretical collaborators, they work really hard. And I'll just tell you the summary of it is what happens is that Now these are because of the structure, right? The kagome is a two-dimensional feature. So because the atoms are arranged in the layers of these kagome layers, there is a lot of fluctuation in the system. That's the Marvin-Wagner theorem tells that in complete two dimension, there cannot be magnetism, right? And which has been challenged recently. But those Marvin-Wagner fluctuations play a role here. At low temperature, these Marvin-Wagner fluctuations are smaller, and therefore they don't play a role. As you increase the temperature, they become more effective, and they start, fluctuating these spirals, and they change the population dynamics of these spirals. So one of the spirals in one direction grows, then in the other direction, and during this process, the scalar spin chirality is formed, and that's how you pick up the Berry curvature, and you get the topological Hall. That's our current understanding. So what we say is that this has a very similar physics as that of this skyrmionic texture, but it is not a skyrmion. It's a dynamical skyrmion where they form momentarily. You cannot capture it with Newton diffraction or any other optical measurement or microscope measurement, but they are there dynamically. Electrons can feel that force, and therefore we can get this extra deflection in the Hall.
What happened to the longitudinal resistivity?
Longitudinal resistivity, it also changes, but by not that much.
It's metallic.
Yeah, longitudinal. This is all metal, and when you apply magnetic field, this happens as a function of magnetic field, right? Mm-hmm. So as a function of magnetic field, it changes a little bit, but that does not impact much. And that model gives a very nice way of calculating these from the experimental parameters, the topological Hall. And when we calculate the topological Hall, this blue one is the theoretical, red one is the experimental. As a function of magnetic field at one particular temperature, it kind of captures it well, and as a function of temperature also it captures it well. So this is our proposal, and that this topological Hall comes from these skyrmionic texture that's not well crystallized yet. They are in the dynamical form. Well, that's interesting, right? It's a kagome system. It has these Dirac bands and so on, and we have this kind of new phenomenon. Okay. Yes.
So, do you know that the transport is largely within the kagome layers and not through the bulk?
This everything was within the layer. Yes. But I will show you here out of plane transport also. Okay, that's exactly this slide. Okay, so here what I'm showing you is just the longitudinal resistivity as a function of temperature and zero magnetic field. This material is even interesting just from this point of view. You look at here, the blue one, when this is in the plane, just as you say, in the plane. Yes.
So what's the effective mass of the carriers?
Effective mass, okay, I don't remember that. I should have known
Is
it.
it large? Or?
No, it's not large.
Okay.
It's not very small. It's not very large. It's of the order of same metals, like maybe 10 or maybe between 10 and 30. Okay. I should have known precisely. I have that information, but just didn't come to my mind. Okay. We have it from both. We did high field magnetic measurement. We did quantum oscillations, SDH, and we have tracked that. We have heat capacity. So we have that information, but just didn't came into my mind. But it's not too small. It's not a heavy fermion either. Okay. So you see this blue curve is when we measure in the plane, and then the red one is when we measure out of the plane. And you see this structure that this is the structure that is above 333 Kelvin. That it's an antiferromagnet, right? It's a collinear antiferromagnet above 333 Kelvin. So there's two layers, spin point in the same direction, another two layer, the spin point in the opposite direction, and so on. And then as you cool below 333 Kelvin, J3 comes into effect, and then it twists these spins, and then you form this spiral state. Okay, that's why this is more sensitive in the formation of these going from here to here. these usually you get these peaks at magnetic ordering. Here at magnetic ordering, you don't see that much. At 350, you see this at 333 Kelvin very nicely. And one thing that if you have noticed here, red curve is always above the blue curve in the magnetic state. That's another interesting feature. Okay, meaning that resistance along c-axis is always larger than in the AB plane, which makes perfect sense, right? Because there are spins that when electron flow into this direction, the electron has to interact with these spins, whereas they don't have to interact when they are moving in this direction, right? So that makes this difference. Now, I'll show you that we can tune this thing by playing with the structure of the material. Okay, that's my next step. Now, yes.
So if you blow up the lower temperature, the flat part.
Yeah.
It's flat all the way down.
Yes, it's flat up to the down to the temperature that we measure. Yes.
Like 4 Kelvin.
Yeah. No, to 1.8.
1.8.
Yeah.
So there's no counter effect in
on this one. No, but if you are interested on the terbium,
okay.
We have seen this condor-like behavior, but we don't understand why it is. That might interest you.
It replaces yttrium
with terbium. I don't have that data. I will talk about that material later,
okay.
but I don't have that data. Since
Same
you asked
structure.
me and you are
Same
interested,
structure.
same structure. You asked me and you have interest in condo. Mm-hmm. We have this a little upturn. We don't understand why this happened. Okay. So on this, now what we did in this one is, see, there are 3 teens here, right? So this is an interesting structure. Now you can, pick one teen, take it out, and put germanium on there, right? That's what we did, okay? And we analyzed our X-ray, and we know exactly on which side there are 3 equivalent sides, like this blue one, or the pink one, or the gray one. It is the gray one that we removed and put here the germanium. Now what it does is that, see, this interaction remains same, but we change this interaction, and we change the other interaction too. So we can actually tune these magnetic interaction by, partial substitution of the germanium atom. And this is what we did in this study. Now what it did, we did neutron on this one. This actually has been, I have not updated, it has been accepted recently to LPJ quantum material, this study. So this is our neutron data. We did all our neutron work. What we found is that, that parent compound first has antiferromagnetic ordering, and then it went into a spiral state. This one orders with the spiral state. So that gave us indication that, okay, something had changed into this system, right? So what had changed is that we determined the magnetic structure of both. So the parent compound structure was like this, if you go into the detail. So in one layer, it is pointing in this direction. In the another layer, there is a negative angle of about 20 degrees. And then you go to the third layer, it rotates by about 90 degrees between this and this. So the effective change between this and this is about 110 degrees. And then it rotates that way, and the rotation completes after about 9 units. It's an incommensurate state. In germanium, what we found is that the rotation angle changes. Okay, the rotation angle changes. Now here, the rotation angle is positive and about 8 degrees. And then here, this is smaller, right? Smaller than this, about 75 degrees, both positive and positive. So definitely, putting that replacing partially, the teen had changed the magnetic interaction. And how it changed, we kind of analyzed this also, that in the parent compound, this J1 was negative, right, ferromagnetic. J2 is antiferromagnetic, and J3 is ferromagnetic. In this case, this becomes, this remains same because J1 is not affected, and then these 2 changes, right, as you expect. And this change, now what they do is that make a significant change in transport property. Okay, what change they did is that these dotted lines are the same data that I showed you earlier of the parent compound, and then these solid lines are for this new compound. Now you see the red one is below the blue one throughout. What does that mean? Is that now conductivity wise, this is more conductive, right? So now all of a sudden, the spiral state has not changed. It remains spiral. There are spins going along the c-axis. But now electrons find easier to move along c-axis than in the AB plane. Okay, why did that happen? And then we did some calculation also. It kind of matches. This is the conductivity ratio as a function of temperature between these two different materials, and we can compare it with theoretical calculation. It's a plasma frequency. Plasma frequency is square of the plasma frequency is proportional to the ratio of c-axis conductivity to the AB plane conductivity. You can see that this one is here, and this one is just the plasma frequency. That's my theoretical collaborator calculated, Igor Mazin. Then here we can see that the c-axis conductivity on this blue one is always larger than the red one, right? Meaning that by changing the Fermi energy, by the change in the by that replacement of the germanium in the Fermi surface, what happened is that it made this compound conductive along c-axis. Actually, we were able to tune this system to make it more conductive along c-axis. That's the story of this. Okay, any question here?
Do we know what how the band structure changed from the
Yes, we know very precisely. We have already published, but that was not a part of what I wanted to talk, so I have not kept it here. Okay, yeah, we have done that very precisely. In yttrium, we have done several different measurements, RPS, high field measurement to track the band structure. In terbium, people have done RPS, so we just published our.
Are there like new states coming up near? Or
there are different states. Yeah, they are different. They are different, but we have not. The little small states will not change this because this is a metal, right? Yeah. So even if there is a small, say a surface state appears, right? That surface state is how much part is that contributing to this conductivity compared to this whole brilliance. So that's not very important for this material. If it was a topological insulator, then it would make a huge difference, right? This is a good metal, so we didn't pay much particular attention to that. 5 minutes. Okay. Oh my God. So now we replace this with the terbium. Then in terbium, what happens is that when you replace this yttrium with terbium, there is one more, ferromagnetic or one more magnetic interaction among these different excited interactions, right? And what it drives now, since I'm running out of time, I'll be fast here. What is one of the highlights? What it happens in this material is that as you cool down, it orders about 425 Kelvin, which is not here because our equipment doesn't go above 400. See, there is a spin reorientation. You can see that when you measure c-axis, the red one is c-axis susceptibility, blue one is the AB plane susceptibility. So there is a reorientation of these spins from this in plane to out of plane at 310. And why does that spin reorientation happen is something that we were interested. Okay, so again, without going into the detail, what happens is that this is the neutron data that was published in this material, that the magnetic moment of manganese doesn't change that much, but terbium changes quite a bit as a function of temperature. And we did a calculation, again, help with from Igor Mazin, that we found that the Weiss field on the manganese atom is much larger than in the Weiss field on the terbium atom. So terbium atom fluctuates more than the manganese atom. And because of that fluctuation, we were able to calculate the manganese anisotropy energy. We can see that the manganese anisotropy energy actually changes here. This becomes equal. This is the magnetic anisotropy of manganese. This is the magnetic anisotropy of the terbium. So at above this place, this negative value means in plane. The positive value is out of plane. Terbium prefers out of plane. Manganese prefers in plane, which was the case of the yttrium, right, when there was no terbium. And then at this point, they become equal. So below this, I forgot to turn off my phone, sorry. And then here, they become equal. And then because of changing of these anisotropy from manganese to terbium wins over and makes it EG-axis ferromagnet or ferrimagnet. And above this temperature, the terbium wins, so the manganese wins over. Okay, that's the whole case. And the interesting thing, So why this spin directness is interesting now is that people found this biskirmic state right at this place. So, actually these things can, this tells me is that actually you can tune these materials, different parameters of these materials. I was talking about non-crystallized fluctuating, this dynamical skyrmion in ytterbium-statistics. Now here you have this biskirmic state forming in the material, right? And we can engineer these materials. Let's forget about this. We can engineer these materials. In thulium manganese-166, we doped with gallium, and see we can reorient these originally the parent compound doesn't have spin reorientation, and then by changing the gallium concentration we can actually engineer this spin reorientation. And we are currently studying whether there is a skyrmionic physics here also or not. So this is kind of engineering the material, and this is a huge system, right? I already told you. And going past from this manganese to vanadium in scandium manganese-166, David Madras actually, David Madras' group found this charge density wave. It's an interesting system. And then Stephen Wilson's group are working on these other vanidates as well. So now I can see that many groups in the US and all around the world are interested in this system and working on this system. So it's a very nice system. And maybe in 2 minutes, I'll kind of steal these 2 minutes because I want to show it to undergraduate students, maybe graduate students also. This is the project that just came from nowhere. So every summer, when I was in George Mason, I used to take high school student, at least one high school student, for internship over the summer. And we had a nearby high school, Thomas Jefferson. Most of my students are from Thomas Jefferson. It's a very good school. And in 2020, when we were still in, or 2021, we were still in COVID time, one student came, Zini Ki. She's now at Michigan doing engineering physics. And I gave her a project because she needed a project for 6 weeks. And these are very smart students. I gave her some tool to how to find two-dimensional material. And then she came to me saying that, oh, I found that this compound, this cobalt dihydride, is a two-dimensional compound. I want to grow it. So I said, grow it. But when she grew and looked at the X-ray pattern, it was not 2D. It's a 3D system. And but anyway, she had to complete her work. She measured it. And then when she measured it, we saw something unusual on this material. Okay, the unusual. This is the crystal that she grew. This is the structure of this material. What we found is that originally we found this linear magnetoresistance at low temperature that becomes quadratic at high temperature. Quadratic is normal magnetic behavior, but where this linear magnetoresistance comes from, it's very small, but it's linear. Was very non-trivial to me. And when we measure magnetic property, it was also interesting because this is the susceptibility. Susceptibility is not like paramagnet. It's not a ferromagnet also. It reminded me of palladium. Palladium does similar stuff, right? And it's very close to quantum criticality. And later we showed that it's a quantum critical system. So the highlight of this thing will be fast here. So then Igor did a lot of band structure calculation here, and what we found is that this looks like a metal, right? There's nothing interesting to it. But if you look into the whole Fermi surface of this material, each of these pointed by arrow, almost everyone except this one and this one, right? Each of them has a direct point over the Fermi surface. So this is a very unusual metal. I've never seen this kind of material having direct point all over the Fermi surface. There are two sets of nodal lines in the Fermi surface in this material. If we can break time ripple symmetry on this one, the expectation is that it should have a huge anomalous form, okay, by doping or something. The quantum criticality is because what we realized is that this is the DFT calculated susceptibility. This is experimental susceptibility. By fitting the Moriarty's fluctuations, putting Moriarty's fluctuation in the system, we could reproduce this experimental one. So we think that, again, I'm being hand waving here because I'm out of time, but we can discuss later if you have questions. That we showed that this is very close to quantum criticality. So maybe we can drive quantum quantum criticality in this system. So these two things, this amazing drag physics and the quantum criticality coming together, might give an interesting system to kind of work further. So that was the story about it. And I kind of talked about these 166 compounds. They are very interesting and very tunable system. And then COT2, it has a very interesting coexisting topological and quantum critical behavior. And a highlight is that it is an example of this exploratory synthesis. You don't have to have some idea. Sometimes just do random synthesis and you can find interesting system also. So with this, I would like to thank you, and I'll take questions.
Yeah, we have time for some questions, Sean.
Your resistivity, some of the material versus temperature looks pretty normal with strong. Well, the resistivity looks like niobium and then titanium. So why don't they go superconducting at the temperature?
I mean, at low temperature, as you say, that rho is rho naught
There
plus
is
something.
nothing that confounding interaction, right?
Yeah.
So why don't they go superconducting?
If I have known
Yeah,
that, then
Manganese.
Okay.
yeah.
So there are enough magnetism.
But this is the makeup, right? You do the same behavior because at low temperature, you froze all the vibrations, right? And then your resistance doesn't change. That's the standard behavior.
So, you mentioned that having Dirac points and then once you gap them out, it kind of gives you a good platform for anomalous quantum halls. Wouldn't you also need some sort of like a flat-ish bands to have like high correlations for that, or is it? I mean, because only Dirac cones are. I don't know whether are they the only necessary reason or gap.
You want to have the edge states, right? Mainly.
Yeah.
Yeah, the edge states you can get in topological insulators without having a flat bands. It has been shown in topological insulator you can quantize the Hall effect. You don't need flat band. Yeah, flat band has their own correlated physics.
Right.
Very interesting, right?
Yeah.
But even without flat band, you can get. I think taking this topological insulator as an example. Yeah, all you need is the edge states. We have an expert here.
So can I ask a question? How sensitive are your measurements to various things that might go wrong, like the stoichiometric, slight errors in the amount of germanium you put in, or things like that?
Especially in doping, or in any of the material.
Sorry?
In one particular material, or in all these materials.
In general.
We can within the limit of our measurement, I can say that they are pretty robust. But we have about 3 to 5% error in our stoichiometry measurement. So that necessarily does not change much property in transport as well as in the magnetic structure.
Like experimentalists don't make mistakes on that kind of.
And I just remember doing some calculations on our anisotropic magnetic system, asking questions. What happens if your applied field is slightly off the anisotropy axis? It makes a huge change.
That's a different story. That's a huge change. Yes.
Exactly. But the stoichiometry, with all the X-ray and stuff, when material physicists show things like this, you don't question that.
Sometimes it happens. Like Kemp and I are working on a system where you have a small change in stoichiometry. It changes the property a lot. But these are pretty robust systems. Yes.
No, it's just that you were talking earlier about all sort of things knobs you could turn.
Yes.
And one of the knobs was how much.
Yes.
And I was just wondering, how sensitive it is.
On this one, stoichiometrically, I have not tried it because in this one always we want to make the perfect structure, and then you can change the elements right? You can change the electron count. You can change the size. That's the knob that we have, right? When I replace germanium with tin, then I'm squeezing that that distance between these two, right? These two layers, because germanium is smaller than the tin. So that's my knob. I kept the electron count same. But when I put gallium into it, I showed briefly that data that I'm changing the electron count also, right? And it gives very different property.
In the topological Hall effect, do you observe these spin polarized currents, or is it like different from the quantum Hall effect?
We do not measure this spin polarized current.
Okay.
Yeah, this is we don't have that ability to do it.
Right, but the topological Hall effect, as you said, is like a non-coplanar effect, right? It's not in the plane of the sample.
Yeah.
Right.
Yeah. When you have scalar spin chirality, electrons, just like as I showed with my hand, this is exactly what happens with the electrons, and they pick up the braid carpets.
Okay, right. Thank you.
Can I ask about like experimental detail, like
Sure.
when you measure topological Hall resistance, how
Yes.
do you distinguish between the anomalous part and the anomalous component and the topological component?
That's a really interesting and very good question. So we scaled the anomalous. Normal is very easy. Especially with anomalous, you need to be very careful whether there is a change in magnetic structure or not. If there is a change in magnetic structure, then you need to be careful because it can change your carrier density also. Okay. If that is not happening, which is the case here, there is no change in magnetic structure. What is happening? What we can do is we can scale it with the magnetization.
Okay. So you measure the magnetization
Right,
first and
right,
scale it.
right. But we have to be careful. In some system, for example, ultramagnets these are the new antiferromagnets. Magnetization is not proportional. The Hall or the anomalous Hall is not proportional to the magnetization. Okay, most of the ferromagnets, just like this one, we can do that because it's not an ultramagnet and there is no change in magnetic structure. Sometimes what happens is that the magnetic structure changes, the magnetization doesn't change that much, and your electronic structure might have changed quite a bit. And in that case, your carrier concentration may be very different, and then you cannot use that. So, a good magnetic knowledge about magnetic structure is needed in order to do that, in which we had already.
Thank you.
All right. It was a good discussion.
Yeah.
Thanks so much.
Yeah. Friends and everybody. I enjoyed the talk. Thank you.